Hello students, welcome to the SWAYAM online lecture series on AI using Prolog. In the last lecture, we saw how supervised machine learning algorithms are used for prediction of a class or a value. And we had also seen the various classification and regression models under the supervised machine learning algorithms. In today's lecture, we will talk about how to evaluate a model. The machine learning models which are built on the data set are always not perfect. They exhibit some error. So, what are these errors and how to find the accuracy of the models are the main topic of this lecture. The basic outline in today's lectures is we will talk about the different type of assumptions which are made by the models, what are errors that are encountered once the model are built, what are bias and the variance, what is underfitting and overfitting, and what are the evaluation parameters used by regression and classification model. In machine learning models are basically they are based on some assumptions, and why these assumptions exist? Basically to ensure that models are valid and they are effective in their performance. What are these assumptions and what are its significance in the ML model? We will talk about this. Now, let us take few models that we discussed in the previous lectures and let us discuss the assumptions made by these models. For example, some of the common assumptions which are made by different machine learning models are as follows. Let us take the first algorithm, a very popular, very simple linear regression algorithm. What are the assumptions in this model? What are the assumptions in this model? The very first assumption is linearity, meaning we assume that there exists a linear relationship between the input and the output variable. That is, whenever a function or a mapping is being predicted by the algorithm, that prediction will be in the straight line manner, and that is a very fundamental and basic assumption known as a linear assumptions, linear relationship between input and output variable. Another assumption is associated with the errors. In the linear regression, it is assumed that the errors of the models are independent. There is no relationship between the errors and they have a constant variance. Another assumption again in this particular model is that independent variable have no correlation amongst themselves. So, these three assumptions are laid down in the linear regression and the model which is built is expected to follow these assumptions. Let us look into the another algorithm, Naive Bayes. Naive Bayes also follows the fundamental assumption of independence of features. Again, it says that input parameters which are given to the algorithm, they are independent of each other. We had discussed in the previous class that the models are fed with independent and dependent variable, input or the output variable. Here it is talking about the input or independent variable. These variables or parameters are independent of each other. This is the very fundamental assumption which is laid down in Naive Bayes. Another very popular supervised machine learning algorithm is support vector machine. In the support vector machine, we have seen in the previous classes that the data is to be separated into two or more classes. It is popularly used for binary classification, and linear separability is the fundamental assumption, meaning that data can be separated into two classes using a linear separable line or a hyperplane. So, the feature space or the input data can be divided into two classes using a straight line or using a hyperplane. Another assumption which is associated with support vector machine is maximum margin, that is the plane or the line which divides the data set into two classes have a maximum margin between them, and that straight line or hyperplane uses this maximum margin to divide the data point into two classes. Let us take another algorithm, decision tree. Decision tree is generally used when the data points are non-linear in nature. That means they do not have a linear relationship. We want to identify a class of a data point, it will traverse the decision tree till the leaf node where the class of the data point is decided. Features used for traversing a tree, these features are again independent of each other. This defines the feature independence assumption of the decision tree model. And there are various such algorithms, some of them they have a very strong assumptions, some have few assumptions. It is very important to note that machine learning algorithms are at times more robust to violations of assumptions than others. It is expected that these algorithms should not violate the assumptions if we have to build a model which performs, which gives a better performance. Additionally, apart from building the models, there are certain pre-processing techniques, or we call it feature engineering, which at times help to reduce this problem of violation of assumptions. It is very important for a person who is developing a machine learning model to understand that the assumptions associated with the models are very important, and they are used to assess whether those assumptions are held in a specific data set or a problem which is being undertaken. So, given a problem domain and given a data set, which machine learning algorithm will perform best under the given data set is always an experimental issue, and knowing the assumptions of each model helps us to decide which model should be selected for a given data set. Talked about the assumption, now let us look into the errors which actually exist in the machine learning model. We know what are errors in an ML machine learning processing. Once a model is developed on a training data set, then this model is fed with the test data. The test data, when fed into a machine learning model, gives a predicted output. We already have an actual value. The difference between the predicted and the actual value defines an error in an ML model. And generally, when the predictions are made by the model, the input is the test data, or it is also known as unknown data. Why? Because machine was never exposed to this data set. So, when we classify the errors in the machine learning model, there are two types. One is reducible and the other is irreducible. We as a machine learning researchers, we can actually enhance or improve our model to reduce the reducible error, but irreducible error are present because of the noise in the data set. If our initial data which we are feeding to the machine learning model contains some noise, then even if we try to enhance our model, even if we make an effort to improve the model, that improvement will not be possible, because error is due to the noise which is present in the data. So, there are certain techniques, not in the machine learning, but in the pre-processing techniques, where we can handle or we can identify this noise, or it can be replaced by some relevant values. So, coming back to the basic reducible errors, we will now talk about what errors can be handled by machine learning algorithm, or by improving its features, or by improving certain parameters. So, there are two types of reducible errors. One is bias and the other is variance. Bias basically defines the error which is introduced into the system when we are trying to approximate a real world problem, which is a complex one, but we solve that problem by using a very simple model. Then we get an error between the expected and the actual value. So, mathematically we define bias as the difference between the expected prediction of the model and the actual true values. Another parameter is the variance. What is variance? When we run our model or when we implement our model on different data set, the amount of variation which is obtained in the prediction is actually the variance. So, let us look into the more details of bias and the variance. Under what condition bias is encountered and under what condition variance is encountered, and how it impacts our machine learning model. Basically, bias is an inability of the algorithm like linear regression to capture the relationship between the data points. See, machine learning algorithms are actually capturing a hidden relation between the input and the output variable. If the algorithm is unable to do, then there will be an error between predicted and actual, and this will give rise to the bias. In other words, it also indicates how far the predictions are from the true values. Bias can be low bias or it can be a high bias. Whenever a model makes fewer assumptions or less assumptions, then the error will be less, and hence the term low bias. High bias models are those where the errors are more, the difference between the expected and the actual value is more. And when this kind of a scenario occurs in our machine learning process, whenever a model is trying to use, or whenever we try to implement a very simple model to solve a complex scenario or a complex problem, then there will be a probability that difference between the expected and the actual value will be more. In other words, we say the system makes a strong assumption about the data and which may not hold true. Each algorithm, definitely when it starts, it begins with some amount of bias, because bias occurs from the assumptions in the model, and these assumptions are related to the target function. A high bias model will never perform well on the new data. A high bias will occur when we have a very good training performance, but not a very good test performance. Let us try to understand this with the help of example. We can see the data predicted, as we can see in the figure. The data is shown with the help of the blue circles. These are the actual data set, and when we are trying to capture the relationship, we capture it in a straight line, which is depicted by the red dots. As it is well depicted, our actual data patterns in the blue circle have some different path, and the predicted line, the red line, which follows the straight line manner, meaning a more complex problem has been modeled in a very simple way. Under this scenario, we get a high bias situations, and this is also known as underfitting of the data. As said, it will happen when predicted model is too simple and our problem is a little bit complicated. It is always recommended that algorithm should have a low bias, obviously because error should be less. Linear algorithms has high bias. That means linear regression which tries to fit a straight line in the given data, there will be high bias, that means there will be more error if the data is not linear. Whereas, if we have a non-linear algorithm, then it will more accurately capture the data path and hence the error will be less or it will have a low bias. Let us take some examples of machine learning algorithms which have low bias, for example, decision tree, k-nearest neighbors, support vector machines. All these are the algorithms which are more complex in nature and hence they fit the data in a better way. Whereas, high bias is generally obtained in linear regression or linear discriminant analysis or logistic regression. They are more simple algorithms and if we try to use them in a complex scenario, bias will be high. So, what a machine learner should do, a person who is trying to fit the model, what ways or what means should be taken to reduce the bias? We can have more input features, increase the input feature, or instead of using a simple linear model, use a more complex model that may solve the problem. Let us now, having talked about the bias, let us now look into what variance is. Now, if we have a model which is built on a training data, the amount of variation which we obtain in this model through different data sets is known as variance. If we create a model with one data, with one training set, we get a prediction. Again, if we fit this or if we predict or if we use this model for another data set, what is the performance? If there is a lot of variation, then variance is high. Generally, it is a very good scenario if we are able to build a model which do not vary too much from one training data set to another. Model which is having a high variance, they give lot of attention to training data and does not perform well on another data which is known as test data. It is also said if a model is not performing well on different types of a data or different set of a data, means that it does not generalize well. As a result, these models they show very good performance on a training set, but they show a very high error rates on the test data. Algorithms which we are trying to implement on a data set, it should be good in interpreting the hidden mapping or the function or the relationship between input and output. Variance are again of two types, a low variance or a high variance. Low variance is a small variation in the prediction of the target function with changes in the training data set. That means, if we are giving different data set to the model, then the error or the variation in the prediction is less and hence we will have a low variance. High variance will occur if the prediction of the target function changes a lot in the different data set. Examples of low variance algorithm are simple algorithms like linear regression, logistic regression and so on. But algorithms which will show a high variance are decision trees, support vector machines and k-nearest neighbors. So, what should we do to reduce the high variance? What we can do is, since the model is more complex, we can try to reduce the input features or we can reduce the number of parameters. Let us not try to use a very complex models, or we can also increase the size of our training data. Let us see what different combinations of bias and variance are there. Algorithms may depict low bias, low variance, high bias, high variance and so on. Low bias, low variance is a very ideal scenario and it is very difficult to achieve. It is not possible that we have an idealistic algorithm. Another combination is low bias and a high variance. Model predictions are generally inconsistent and accurate on an average. What happens when there is a high variance? Model basically is said to perform very well on the training data, but it does not perform well on the test data. So, hence the variance is high. Another combination is high bias and low variance. When do we have a high bias? High bias will occur if there is a lot of gap between the predicted and the actual value. Problem is complex, but we are using a simple model. So, again this is also a case of it is an undesirable case. And lastly is high bias and high variance. Here the predictions will be again inconsistent and it is not preferred at all. So, in practical scenarios we will either get a high bias low variance or we will get a high variance low bias. As we can see in the graph, whenever there is a training error, the training error is low, but the test errors are high. So, we can see there is a difference between the training error and the test error. So, this is a region of high variance, whereas in the case of high bias scenario, training and testing are almost similar. So, in a machine learning model, we have high bias and high variance, or high bias, low variance, low bias and high variance. It is very essential to maintain a balance between these two parameters. Whenever we have a high bias, it introduces underfitting in the models, and high variance introduces overfitting. What are these terms and the concepts of overfitting and underfitting? Let us try to understand this, because whenever we are building a machine learning model, it is a preferred parameter that model should not underfit or model should never overfit. There has to be a balance. So, when underfitting occurs, whenever there is a high bias, underfitting will occur whenever there is a high bias, meaning we have a complex problem and we are using a very simple model. So, and at times also when we use a very small amount of data to train the model, then also we get this type of a scenario of underfitting. Examples of underfitting models are linear regression, logistic regression. Next is overfitting. When overfitting occurs in the machine learning algorithm? When our model captures noise along with the pattern. So, if the noise is present in the data, the model will learn the noise also. If the model is learning along with the noise, then model may perform well in during the training, but it will not perform that better or that well during with the test data. So, under this scenario, we will have high variance and model is set to overfit. These models are very complex, like decision trees, and these decision trees are prone to overfit. So, as we can see the three figures for overfitting and underfitting, in the very first case model is underfit, as simple linear model is used and the bias is high. Look into the third figure, it fits the data well. It fits the data well with the training sample, but will not show good results with the test data, because it has learned the noise also. So, this was the case of overfit, high variance. The middle figure, where we find the model is just a perfect fit of the data, and this is what is expected when we build a machine learning model on a given data set. While building the machine learning model, it is very important to take care of bias, variance and overfitting and underfitting. Model should neither be overfit or it should not be underfit. If the model is very simple with fewer parameters, it may have low variance and high bias. If model has a large number of parameters, it will have high variance and low bias. So, it is essential to maintain a balance between bias and the variance, and this balance is known as bias variance trade-off. Any algorithm which is implemented on a data set must maintain this balance between the two, and The model should not be either overfit or it should not be underfit. Algorithm cannot be very complex or less complex at the same time. To build an effective model, a good balance between these parameters is required, so that the total error is minimum. The optimum balance of bias and variance would never overfit or underfit the model. As we can see in the figure, as the complexity of the algorithm, along with the complexity of the algorithm, the bias reduces and the variance increases. But at some point, these two values are optimum in nature, as shown in the figure. And every algorithm, most of the machine learning algorithm should try to obtain that minimum point while training the model with the data set. Having talked about the bias variance trade off, let us look now into different techniques which are used to evaluate these models. In the supervised machine learning algorithm, we have talked about two tasks, one the classification task and the other was the regression task. So, various parameters are used for each of these tasks. To evaluate a classification model, confusion matrix, accuracy, precision and recall are popularly used, whereas for regression model, where we are predicting a continuous value, sum of a square of error, the mean square error, root mean square error, the mean absolute error are used to evaluate the model. Let us now look into these evaluation methods. We will first discuss the classification errors, and the classification errors are very well depicted with the help of a matrix, and that matrix is known as confusion matrix. Another term for this confusion matrix is error matrix. This matrix is basically used to find out the accuracy, the precision, the recall, the F score and etc. All these are parameters to evaluate a model, a classification model. So, what is confusion matrix? As said, it is an error matrix or it is a table, and this table allows us to visualize the performance of an algorithm, especially the supervised machine learning algorithm. To understand the confusion matrix, let us take an example of a two-class classification problem. Let us say a problem where we need to classify a data has two possible outcomes. One is positive and the other is negative. It can be in a medical diagnostic system or it can be a sentiment analysis problem. So, given a data point, the objective of the algorithm is to predict that whether that data point is positive or it is negative. So, what we will do is, now we will plot the predicted values against the actual ones and we get a matrix. So, we had the model, we took the test data, we got the prediction and that prediction was either positive or negative. Whatever predictions we achieved and whatever actual values we had, we are now going to construct a confusion matrix. This confusion matrix will have columns or will have the actual values and in the row we will have the predicted values, and each of the cell will be known as true positive, true negative, false positive and false negative. If a model predicts how many data points were positive and actually how many data points were actually positive, then that cell defines the true positive. So, true positive are the data points whose actual outcomes were positive and algorithm correctly identified them as a positive. True negative are the data points whose outcomes are actually negative and algorithm correctly identified it as a negative. False positive is the value or those count of those data points whose actual outcomes are negative but algorithm incorrectly predicted as a positive. False negative are the data points whose actual outcomes were positive, but the algorithm incorrectly identified it as a negative. As we can see, the goal of evaluating a model using the confusion matrix is to maximize the true positive and the true negative, and to minimize the incorrect prediction, which is false positive and false negative. Let us understand this confusion matrix with the help of an example of heart disease. A patient is having a heart disease, yes or no, positive or negative. These are the two possible outcomes. Let us say out of 200 test data which was given to the model, a classifier model, true positive were 20. So, how do we interpret 2 positive 20? 20 are the data points of the patients which were predicted by the model as having a heart disease, and they were actually having heart disease. True negative is 130. The classifier has correctly identified that these 130 is not having heart disease, and they were actually not having heart disease. Likewise, false positive is 30 and false negative is 20. These are incorrectly classified data points. Based on true positive, true negative, false positive, false negative, parameters like precision, recall and F1 scores are defined. Precision, recall are very important to evaluate the classification model. So, how do we define a precision? It is that fraction of the relevant instances amongst the retrieved, meaning let us say if there are 100 patients which are actually having a heart disease, and our model predicts 80 of them as correctly. So, 80 by basically we say 80 by total, 80 by 100 is basically the precision. Another important known as R, recall value or sensitivity, is the fraction of total amount of relevant instances that were actually retrieved. So, how do we define a recall? Basically the total where let us say out of the total values, how many correctly were identified by the model. And accuracy, we define it as a fraction of total instances correctly classified by learning model. That is, we say true positive plus true negative divided by all the 4 values, that is the accuracy. Error is false positive plus false negative divided by total 4 cells values. Let us see how do we calculate in our given example. So, we have a heart disease, person having heart disease, person not having heart disease. The values are given in the respective cell. As we can see, the true positive here is 20, true negative is 130, then false positive is 30 and false negative is 20. Based on this, we can calculate the precision, the recall, the accuracy, the misclassification rate and the F1 score. So, we have seen precision and the recall, they are very important to evaluate the algorithm, but what happens when we try to compare different algorithms, the performance of different algorithms on the same data set, we need a value. Precision and recall alone are not enough or sufficient. So, we use F1 score to compare all the algorithms and find out which algorithm will perform best for in the given data set. So, what is F1 score? F1 score is nothing but it is a harmonic mean of precision and recall and or weighted average. As we can see in the formula, we can calculate the F1 score as given in the slide, and the value of F1 score is between 0 and 1. The values which are nearer to the 0 indicates a not very good performing algorithm, whereas algorithms which are showing a higher values or towards 1 are the better algorithms. Apart from F1 score, there are other parameters which are used to evaluate the algorithm. For example, sensitivity which is also known as recall, the true positive rate, is also known as recall. Another parameter is specificity, which is true negative rate, then false positive rate and false negative rate. Formula is as given in the slide. Some of these parameters are plotted in a graph, and the behavior of that graph is also helpful in analyzing an algorithm. A very popular graph which is known as ROC, or we call it as receiver operating characteristic graph. It started in electronics signal detection in 1940s and 50s. It also became popular in biomedical applications, but currently it is very popular to evaluate the machine learning algorithm. So, let us try to understand what this ROC curve is. It is actually a graph which is plotted between the true positive rate on the y axis and false positive rate on the x axis. ROC curve with high TPR and low FPR are the models which represent high TPR and low FPR are better models as shown in the figure. That means, when we plot a graph, when we plot an ROC graph, if that graph is pulled towards the upper right corner, that means we are having a higher TPR and a low false positive rate, and which is a preferred scenario. So, any algorithms which is more pulled towards the higher TPR will be the algorithms which are performing better as compared to the others. A perfect ROC is shown in the figure. We can see that the value is 1, that means it is an idealistic scenario which is not possible in the real time applications. The real time application graph is shown just below the idealistic one. Another important parameter is an AUC, which is an area under the curve. When we plot an ROC curve, the area under that curve, known as AUC, also is a parameter to evaluate the algorithm, and generally that area is between 0 and 1. The higher the value of AUC, the better is the algorithm. TPR again should be high. So, generally if AUC values are towards 1 like 0.7 or 0.8, then those algorithms are expected to show the better results. So, now we have seen a classification model, evaluation techniques, that is a confusion matrix, the F1 score, the precision, the recall, the ROC and the AUC curve. Let us talk about how the regression model will be evaluated. Some of the common parameters which are used for evaluating the regression model are mean absolute error, mean square error, root mean square error and so on. Let us take one of these parameters one by one. Mean absolute error is represented by the difference between the original and the predicted values extracted by their averaged and absolute difference. You take the difference, take the absolute value of the difference, sum up all the difference of the different data points and average them, that is mean absolute error. So, mean square error is again the difference between the actual value and the predicted value. Take a square of that value, add up all these squares, find out the average. Root mean square is under square root of MSE is a RMSE, and R square is coefficient of determination. It basically represents how well the value fits as compared to the original values, and generally it is ranging from 0 to 1. Again, higher values represents a better model. Formula for this is given in the slide. So, what we have discussed in the today's lecture? We have talked about the assumptions in the supervised machine learning algorithms, what are different types of errors, what are bias and the variances, what is underfitting and the overfitting and how to handle them, what are different evaluation parameters for the classification model, and what are various evaluation parameters for the regression model. I hope you understood and enjoyed this lecture. Thank you once again.